Selamat siang, Mas Tata, Bu Sari.
Ya, selamat siang. Assalamualaikum.
Salam.
Selamat siang.
Bentar aku ngeset itu virtualnya. Ini di sana jam berapa ya, Mbak Tika?
Kalau
Sesi berapa jam ya?
di Bangladesh 1 jam lebih awal, Bu. Jam berapa ya? Jam 12, lebih 12.
Jam
12.
Hanya beda 1 jam?
Iya, beda 1 jam lebih awal.
Gitu ya?
Iya.
Bangladesh. Ini di sana jam berapa ya, Mbak Tika?
Jam 12.
Berapa jam ya?
12.
Aku nge-lag ya kayaknya ya. Suaraku kok bisa, aku aneh. Padahal tadi sudah ini terus keluar lagi suaranya. Kenapa? Kayaknya beda 1 jam.
Iya,
Tuh kan? Gitu ya? Keluar lagi suaranya.
Kok suaranya begini ya? Kenapa?
Ini di sana jam berapa ya, Mbak Tika?
Jam 12.
Berapa jam ya?
12.
Apa itu?
Apa ini?
Bisa aku aneh. Padahal tadi udah ini terus keluar lagi suaranya. Ini keluar dari siapa ini? Keluar dari laptopnya siapa ini?
Semuanya, Bu, kayaknya.
Suaranya.
Mengulang. Suaranya begini ya? Minta tolong siapa ini?
Apa itu?
Apa ini?
Bisa. Padahal tadi udah ini terus keluar lagi suaranya. Ini keluar dari siapa ini? Keluar dari laptopnya siapa ini?
Semuanya, Bu, kayaknya.
Suaranya.
Mengulang. Dari saya, jangan-jangan. Mas Lutfi ada nggak ya? Oke.
Ini keluar dari siapa ini? Keluar dari laptopnya siapa?
Semuanya, Bu, kayaknya. Mengulang. Dari saya, jangan-jangan. Mas Lutfi ada nggak ya? Oke.
Oh, audionya di setting apa ya? Speaker, audio setting.
Ini saya telepon Mas Lutfi, minta tolong sebentar, kurang paham. Aduh, ini speakernya sudah minta join.
Speakernya?
Iya. Oh, udah nggak nge-lag ya, Bu ya?
Enggak.
Oh, oke. Kenapa tadi? Jadi
Tadi juga bukan nge-lag ya, tadi itu kok keulang-ulang karena beberapa kali gitu kan ya.
Iya. Ini saya telepon Mas Lutfi.
Tuh, ini keluar lagi nih.
Ada lagi, kenapa ya? Ini speakernya sudah minta join.
Speakernya?
Ya. Oh, udah nggak nge-lag ya, Bu ya?
Enggak.
Waduh, ngulang lagi ya.
Tadi juga bukan nge-lag ya, tadi itu kok keulang-ulang karena beberapa kali gitu kan ya. Tuh, ini keluar lagi nih.
Ada lagi ya.
Oh, keluar dulu dah. Audio.
Coba lagi, Mbak.
Gimana Mas Lutfi?
Oh, masih mengulang-ulang nggak? Masih ada suara yang menggema nggak?
Bukan menggema sih, jadi yang sudah itu terulang kayak record terus di iniin lagi gitu.
Oh, oke. Saya tahu ininya, Bu. Kayaknya dari ini.
Jadi yang sudah terrecord kan itu terus di ini lagi, diputar lagi. Ini hostnya siapa?
Hostnya Mbak Tika.
Saya
Oh,
sekarang. Gimana Mas Lutfi?
Yang jadi semuanya dijadiin host aja, Mbak. Yang di sini ada Mbak Rati.
itu terulang
Jadiin
kayak
co-host.
terus di iniin lagi gitu.
Oke, ini aku buat co-host.
Oh iya, masih ada yang mau.
Iya, ini udah co-host. Record kan itu terus di ini lagi, diputar lagi. Ini hostnya siapa?
Hostnya Mbak Tika.
Saya sekarang. Gimana Mas Lutfi?
Yang jadi semuanya dijadiin host aja, Mbak. Yang di sini ada Mbak Rati.
Itu terulang.
Apa ada yang lagi buka live stream juga, Kak?
Ini YouTube soalnya ya? YouTube-nya sudah ya?
Iya, Bu. Soalnya udah, tapi yang di komputer yang di sini udah saya tutup sih.
Oh, kayaknya gara-gara YouTube deh Mas ini. Sorry.
Kenapa?
Ini Bu, YouTube-nya tadi saya coba cek kan, sepertinya gara-gara YouTube terbuka. Maaf, udah solve. Mengerti.
Oke.
Jadi sekarang YouTube-nya gimana?
YouTube-nya
Oh,
masih live stream tapi di mute
Di
juga
laptop
masih
saya
ini.
mute ya. Harus sadar. Oke, thank you Mas Lutfi.
Oh,
Oke,
I
siap.
see. YouTube-nya kan memang lambat ya.
Iya, betul.
YouTube-nya lebih lambat.
Mohon maaf. Sebentar, ini ada yang ini speaker saya masukkan saja Bu ya.
Boleh.
Oke.
Panggilannya siapa?
Charmin.
Sarmin.
Iya.
Dia memang kuliah sama-sama di ini dulu.
Iya, Bu.
Di
Saya S2, dia S3 pada saat itu.
Oh, I see.
Ini. Halo, Charmin. Are you here? Charmin. Masih di mute. Oh.
Hello.
Halo.
Halo.
Genki.
Hai, Genki. Anak tua?
Genki desho. Sashiburi.
Hello, Dr. Sarmin.
Hello.
Yeah, I'm Retno Sari.
How have you been? How are you?
I'm fine. Domo. Actually, I can speak a little bit Japanese.
Me also a very little bit Japanese. I think
Really?
Dr. Prastika is very much fluent on Japanese. I think.
How is in Bangladesh now?
We are still on the emergency condition. It's still lockdown, so everything is closed. Only like medicine shop or some grocery shop are open, so everything is closed everywhere. COVID cases is increasing day by day, and
Increasing?
Increasing, and death is also increasing. Number of deaths every day, so not so good.
Yeah.
The school also closed, right? University.
Everything, almost all office except some like medicine shop, hospitals. This type of office are open, and transportation. Moving from one town to another town is blocked. We cannot go from one city to another city right now.
Oh, really?
Yeah, transport. We are just in home, everybody.
So you work from home now?
Yeah, work from home. every day.
Mhm.
So
Yeah, it's already more than 1 year. And
yeah, in the meantime, there was everything was open, and then the number of cases increasing, so everything need to shut down again.
I see. Yeah. Like, India is really what we call Hidoi nih. Hidoi nih. India.
Yeah, now India is increasing. The number of COVID cases is very much increased in India.
India. It's not so far, right? Bangladesh, right?
Mm-hmm.
Well, anyway, we can meet here.
Yeah.
It's really good thing. Yeah, I don't remember how many years we didn't meet each other. I mean, after you finish PhD and then you continue postdoctoral, right? In Nagano?
Nagano, yes, from maybe 2017. I met you last time, I hope.
Yeah.
So
4 years.
Yeah,
almost
3 to 4 years, right? Yeah. And then I continue PhD, but you're doing postdoctoral in Nagano, so we didn't meet each other at the time. So it's really good here, meet by online anyway.
there's
You're still contacting Professor Katayama?
sometimes very rare, not so often.
Still working with ionic liquid, right?
No, now I have little bit shifted because due to economic problem, we can't buy ionic liquid right now. So I am just working with some aqueous system, and I little bit shift to like a drug surfactant system, not electrochemistry anymore. But I will. I hope. I hope. But I can start soon.
そっか、残念ですね。But we're still working with outcome. That's good. Yeah.
We also have here Dr. Tahta. Is
Hello.
now at where is it? Sendai.
I'm in
Sendai.
Tokyo University.
I see.
Yeah, doing his postdoc for two years.
2 years. That's right.
Yeah.
This is my second year already.
Second year.
But the COVID case in Japanese also increased. I heard about that.
Yeah, still increasing.
Iya benar ya Pak Tata ya.
Yeah. Continuously increases.
Yeah.
Oh. Participant is already answered.
How many students will join this
All the
seminar?
students, 80 students from nanotechnology engineering, and then there are several participants outside our study program. Okay. So we will wait until 1:30, so 5 minutes, and then we will start.
Maybe Dr. Samin can try to share share screen.
Can you see the screen?
Yes, we can. That's good.
Okay.
Why virtual background is not working in my PC? It's just not.
Maybe the light.
It's okay.
It's okay. No problem.
It's just for like a short screen. It working.
So, it's dangerous. My language become mixed now in English and Japanese.
In my case too, it mixed of Bengali and like English. Not so many Japanese.
So, and in Bangladesh, what's language? It's the
Uh,
same. Yeah?
Bengali, it's it's almost similar to Hindi, but not
Uh-huh.
exactly.
Oh.
Some pronunciation is same, but the writing is very different from us. Maybe pronunciations and meaning of the word is almost same, but the writing processes and grammar is different from us in Hindi, Indian language.
Okay. So the character is Hindi character? No?
Karata? I don't
Yeah.
know.
Well, like katakana, hiragana, the character. You write
No,
in...
Oh, no, it's just different. Just pronunciations is almost same, and sometimes meaning is same, but the writing character is
character is different.
Is a difference. Yeah.
Musukasi nih.
Muzakashi.
In Java, we also have Japanese character, but we don't use it anymore, ya.
Yeah.
Plastika.
Elementary school. Yeah.
So you use Indonesia language, or you have another language? Indonesia have
yeah, national language is Indonesian, but we have like local, what we say, like Java.
Yeah, there are
and many dialect.
more than 1,000 languages.
Yeah.
It depends on district, area to area.
That's
so it
right.
changes.
That's right.
Yes.
Yes. Okay. Yeah, 2 minutes.
Okay. Ini ada akreditasi juga, Bu pasti.
Iya, Bu. Ya, saya belum bisa join. Takut ke mix.
Iya, makanya saya 2 deh. Mana ya? Jatuh. Mahasiswa kita sendiri berapa? 80 something.
81.
80 pas ya? 81 ya?
81.
.30 apa kita mulai saja ya Bu ya? Okay, I think we should start. Okay. Can we start? Charmin, okay?
Yeah, sure.
Thank you. Okay, good afternoon, everyone. Welcome to our webinar, a video conferencing with Universitas Airlangga entitled Voltammetry Data Processing. We have Dr. Charmin Sultana from the Department of Chemistry, Maulana Bashani Science and Technology University, Bangladesh, as a speaker today. And I'm Prasika. I'm a lecturer in the Nanotechnology Engineering Faculty of Science, Faculty of Advanced Technology and Multidiscipline, Universitas Airlangga. So I thank you very much for all the participants that are coming to this webinar. And I also thank you for all the teaching staff and the lecturers, the dean, the coordinator from the Faculty of Advanced Technology and Multidiscipline, Universitas Airlangga. So before we proceed to our main session, we would love to hear maybe one or two words from our Nanotechnology Engineering Study Program Coordinator, Dr. Retno Sari. Dr. Retno Sari, it's okay? Dr. Retno Sari?
Ya,
Okay, it's yours.
baik. Terima kasih, Bu Tika. Thank you. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon and welcome to all members of FTMM, Faculty of Advanced Technology and Multidiscipline, for the lectures and also the student. And I would like to extend my special warm welcome to our guest lecturer from the Faculty of Science, Maulana Bashani, Science and Technology University Bangladesh, Dr. Sarmin Sultana. This is the first DECOTA video conference conducted by Nanotechnology Engineering Study Program. For your information, Dr. Sarmin, DECOTA is a university program that invites international academics to deliver online course, guest lecture, and also writing clinic in seminar class. We are thankful to Dr. Sharmin for taking the time out of her busy schedule to share her expertise about voltammetry data processing, right?
Yeah.
I do hope that the topic would help the students to expand and enhance their knowledge. And I also encourage the student to take part during the discussion session. Thank you, Dr. Sharmin. And thank you for all of the students for joining this DECOTA. Wassalamualaikum warahmatullahi wabarakatuh. Terima kasih, Bu Tika.
Thank you very much, Dr. Matari. Okay, so before we proceed to our main session, I would love to read Dr. Sharmin CV. So for the information, Dr. Sarmin Sultana is from Department of Chemistry. So she is a lecturer at the Faculty of Science, Maulana Bashani Science and Technology, University, Bangladesh. So she has an interest in research about electrodeposition, batteries, supercapacitor, ionic liquid, and also nanochemistry. Before, she's working as a postdoctoral researcher in the Department of Chemistry and Materials, Faculty of Textile Science and Technology, Shinzu University, Nagano, and then now become a lecturer in Maulana Bashani Science and Technology University, Bangladesh. And Dr. Sharmin Sultana graduated from University of Dhaka, Bangladesh, as a Bachelor of Science with honors in chemistry, and then continue in master degree from the same university, University of Dhaka, Bangladesh. And in 2017, he continued in Keio University, Japan, for PhD in Graduate School of Science and Technology, School of Integrated Design Engineering, Department of Applied Chemistry. So she already published many publications, especially in the electrochemistry, measuring special in the nanoparticles or metal nanoparticles deposition and preparations in ionic liquid. So I think she's already an expert to explain the basic concept of voltammetry data processing today. Okay, so that's all. Dr. Sharmin, are you ready?
Yeah, thank you.
Okay, please, time is yours.
Yeah. Thank you, Dr. Prostika and Dr. Sari and all other who can you hear? Sorry, there is
yeah, no problem. Yeah, please.
Here showing some interrupted. Okay, thank you everyone who joined this meeting, and this is Dr. Sharmin from Bangladesh, and you already know about that I'm working as a lecturer at Department of Chemistry, Maulana Bashani Science and Technology University. So thank you for your kind introduction, Prostika. So I will continue my lectures from now. So hope you will enjoy this lecture and we will have a fruitful discussion afterward. Okay, so before going to voltammetry, we just start with electroanalysis. What is electroanalysis? So electroanalysis is sometimes we also named is or referred is as voltammetric analysis, which is very important to characterize electrochemical or redox properties in inorganic or organic molecules or compounds. So electroanalysis actually based on, we have to research on the what's happening on a metal electrode and solution of or electrolyte in the interface. We basically focus on this region, on this design. So in voltammetry, what we measure is current as a function of voltage or electrode potential, or more specifically the working electrode where our interest reaction is occurring. So electroanalysis can be classified into according to their measuring transport properties, or like electrochemical equilibrium or electron transfer process. So if we are using like transport properties of ion, we have conductometry, as you can see here. And if we are considering electrochemical equilibrium or electron transfer or charge transfer process at the interface, we have two different models. One is referred as static methods and another is dynamic methods. So today we basically focus on these electrodynamic methods, which we can also divide it as control potential methods and control current methods. And control potential method can also be subdivided into some other group like control potential coulometry, voltammetry. It could be linear shape voltammetry, cyclic voltammetry, and amperometry, chronoamperometry, and impedance spectroscopy. And for control current methods, where the subdivision can be referred as control current coulometry and chronopotentiometry. So today we will only focus on control potential method, especially voltammetric method, including linear cyclic voltammetry and cyclic voltammetry, and also we will see chronoamperometry, chronocoulometry, and also we will see the pulse technique, which is also a classification of potential step techniques. So let's have the definition of Faradaic and capacitive current. We need to know this because we are now considering the electroactive species. We have to analyze the analyte. So we need to know what type of current we are measuring, especially when Faradaic current, which is referred to the oxidation or reduction, the current due to the electron transfer, which causes the oxidation or reduction at the electrode surface. In contrast, the capacitive current, you may see here, that non-Faradaic current, which contribute to the charging of double layer capacitance. Now, what is double layer? Whenever now have a look on this left-hand side pictures or skin. So when we immerse a metal on a electrolyte solution on the vicinity, on the very vicinity of the metal electrode, we have the solvent molecule, and there will be some specific absorbed anion. And this, if we imagine as imaginary plane passing through the center of the specifically absorbed anion, which is known as inner Helmholtz plane. And then to the very next of the inner Helmholtz plane, we have solvated cations or solvated anion, depending on the how electrode is polarized. If we see electrode is negatively polarized, then we can expect the nearest layer of the solvated ion will be the solvated cations. And if we imagine a plane through the center of the solvated ion, we will have another plane which is known as outer Helmholtz plane. And then we will have the diffuse solvated cation, solvent molecules, and specific absorbed an anion in the solution. And this region will be named as diffusion layer. So the electron transfer reaction will be held. We can see the very next figure at the interface, at the electrode surface or interface between the electrode and electrolyte layer. And then how the analyte will pass from the bulk solution, from the region where the analyte is little bit far from this region, compact double layer region. There will be different method how the analyte will migrate from this bulk solution region to this interface region. They could be, and the current response will be proportional to the diffusion flux of the analyte. So this process, the diffusion of this process or the mass transport can be divided into three classes, which is known as diffusion, migration. Diffusion is due to the concentration gradient, as when the electrode is polarized, the analyte will be oxidized or reduced regarding how electrode is polarized. And migration due to the Coulombic interaction, electrostatic field, the analyte will move to the bulk, to the electrode surface, and there will be convection. There are some natural convection, some vibrations, or some rotation is present there, so it can proceed. So to improve, to analyze or to improve the signal of a voltammetric signal, it is necessary to improve the ratio of Faradic to capacitive current when the analyte concentration is very low. And next we will see using voltammetry, we can detect analyte concentration down to 10⁻⁸ molar. So this amount is very tiny, and we can detect very trace metal, heavy metals, and also organic compounds. So now we can discuss with where our interest reaction is occurring. We will use an electrochemical cell to analyze our compounds, and that electrochemical cell is actually a cell. It could be a beaker, it could be a cell, it could be a setup where metal electrode is dipped into an electrolyte which contains our analyte, and which generates the electric current, which either generate or use electric current. So in this figure, you can see there are 3 electrode cell setup, one of which is working electrode, where the actual reaction, oxidation or reduction is occurred, and there will be auxiliary electrode, and there will be reference electrode. And this type of system is known as 3 electrode system, and there is another system which contains 2 electrode system, which use one working electrode and another is auxiliary, or which can be referred as reference electrode 2. So to supply current or potential to control the potential or current, there are 2 types of instrument. One is potentiostat, another is galvanostat. And what is potentiostat? Potentiostat actually control the voltage across auxiliary electrode and working electrode, and another part, reference electrode, just adjust the voltage between working and reference electrode. So that we have to choose that reference electrode very precisely, so that the potential of the reference electrode do not change, or current do not pass through the reference electrode. And And then the next section is galvanostate, where the control current is, we use control current and we measure the potential as a function of current. Now have a look at how many ways we can do voltammetry to analyze our samples. And there, the first category goes to linear sweep voltammetry, and second is cyclic voltammetry, and third we will discuss potential step, which can be also classified as pulse voltammetry. And what we will need to carry out an experiment is that we need an electrode. We need the electrode, it could be an inert metal, and now we are using carbon electrode as well, like glassy carbon, diamond, and many other electrode. And solvents. We need a solvent at which our chemical will be dissolved, and this solvent mostly we can use which have high dielectric constant. It could be aqueous or organic or even ionic liquid. And a background electrolyte or a supporting electrolyte, which we use normally an inertial on the measured potential window. So we will work in a potential range. In that potential range, the background electrolyte should not oxidize or reduce. So what kind of background electrolyte we can use is like sodium chloride, tetrabutyl ammonium perchlorate, or any other salt as well. And finally, the reactant, which we will gonna analyze the redox properties of the reactants, the kinetics, electrokinetics of the reactants, and that concentration is about millimolar range. Now let's start with linear sweep voltammetry, which is abbreviated as LSV. And what it do is we apply an initial potential and we scan this potential only one direction to reach a final potential. And now consider we are reading the reaction of a very simple reaction O plus Ne2R. A compound O, a species O is accepting electron, and reduction is happening and producing product R. So in that case, we will sweep that from initial to final potential at a sweeping rate which ranging from 10 millivolts per second or 2,000 volts per second for conventional electrodes. If we choose microelectrodes, which have the diameter in a micrometer range, that scan rate could be much more values. So when we are sweeping at a constant rate from initial to final, how the response will become. So now have a look at the response I versus E curve with current versus potential curve. And this potential is, obviously we control this potential or supply this potential by using a very good precise potentiostat. And we measure the current as a function of potential. So this response is, we can see there is a peak shape response, and it can be a static, steady state depending on some conditions like viscosity of media, molecular mass of the analyte, scan rate, and any other many other factors. It can be a static response as well. So when the response is static, the current can be measured. The peak static current by steady state current can be measured using these equations, and we will see what every parameter means, and we can see the meaning of each parameter. And for peak shape voltammogram, the peak current equation will follow. Sorry, this will be 10 power 5. There is a mistake. 10, not it's 105, 10 power 5. And this equation. So using these two equations, we can calculate, from using this equation, we can easily calculate, from here we can calculate diffusion coefficient, and from this equation, if we plot peak current versus square root of scan rate, we will have a slope, and from this slope, we can actually calculate diffusion coefficient, which measure how much analyte can pass per centimeter area per unit time. So now let me explain what region actually represents what. So when we choose an initial potential, which means we have to set this initial potential in the region where no Faraday process occurs, or in the other word, where no electron transfer or reduction or oxidation is occurring. And then we will sweep the electrode potential more negative when are considering reduction, more negative, so that it passes the favorable thermodynamic potential or equilibrium reversible potential, where actually the reduction occurs. Reduction is favorable thermodynamically, and then we will continue to apply more negative potential. So now look at the response here. When the potential is not enough to reduce the analyte, we will see very small change in current, or almost zero current. And then when the reduction is enough to electrochemically active the analyte and reduction is begin, so we will see a sharp increase in the current, and once the equilibrium potential is reached, and we will continue to, once the equilibrium is reached, we will see a peak shape is arrived, and after that there is fall of the current. So until this region, when the reduction current is very increasing exponentially, this region we can show is due to the electrode kinetics, and the peak shape is due to the mass transport region, which is solely controlled by diffusion of analyte from bulk to the electrode surface, and this rate is decay with time, because there is a depletion of diffusion layer, and with time it will thickening the diffusion layer, and we will see the falling of current in the signal. So from a signal of LSB, one can easily tell what is going on there. Is it due to the electrode kinetics? Is it due to the potential diffusion controlled or mass transport process? And we can hence comment on the reactivity, comment on the kinetics of the electrochemical reaction. Now, what type of diagnostic information we can have? So if we gradually do a series of experiments of the same analyte, and we change the scan rate of measurement from when we sweep from initial potential to final potential, and we use different scan rate, we will see with increasing scan rate, the peak current will increase. And it is very much expected, because as we see, the peak current is due to the flux of the analyte from the bulk to the electrode surface, and it depends on concentration gradient of the reaction. So at when very first scan rate is applied, and there is no time to deplete the diffusion layer, and this the diffusion layer thickness will be very much thin compared to the very slow scan rate. When we apply very longer time, and then there is the depletion of diffusion layer, and thickness of the layer will increase. So concentration gradient will decrease. And we can, from these characteristics, we can see, if we see the increasing trend, and we can plot the peak current versus square root of scan rate, and we will calculate the parameter like diffusion coefficients and other parameter as well. So very similar to LSB, there is another technique which is called cyclic voltammetry, which is potential dynamic techniques which apply a cyclic potential to working electrode. What does it mean? It means we go from a initial potential to a maximum potential where the analyte is oxidized or reduced, and then we return to another minimum potential where the product is reoxidized or re-reduced depending on the preceding reactions. So we can easily check the reversibility, irreversibility, or quasi-reversibility of the system, and we can also check the electrode kinetics, and we can determine the concentration of the analyte, and we can also determine many other electrochemical parameters like half-wave potentials or like diffusion coefficient and other peak current, this or peak potential, peak current, diffusion coefficient, half-wave potential. So we can calculate from determining the Prastika, did you change? There are some.
Yeah, it's not
okay. I see some request here. Sorry, due to interruptions. So this figure, if Dr. Prastika can show some interface of like potentiostat, we can show how we select this initial potential, sweep rate, maximum potential, minimum potential, and final potential. So it will help a student to how actually we input our data and how actually we see the response, and we can analyze the system, whether the system is reversible, irreversible, or quasi-reversible, or how the electrode kinetics is that the kinetics is faster kinetics, or is the kinetics is sluggish, or we can see in between as well. So so now have a look how a typical cyclic voltammogram look like. So before seeing the signal, we just show a cycle of cyclic voltammogram. We will go a forward scan from a initial to final potential where the product is where the analyte is oxidized or reduced, and we will go back to the initial potential, and we call this scan is reverse scan, and this potential where the one cycle is complete, and we can go more cycle with this experiment, and this vision where some cycle is complete, we can name is at switching potential. And cyclic voltammetry for a single cycle, it is like a triangular potential excitation, and we will see the response like this. Now, if we consider we are going from initial to final, from a positive value to a very negative value, which is more negative than reversible equilibrium potential or thermodynamically favorable potential, for a redox couple, and we will see the reduction is happening in the forward scan. And again, we can, this peak is all on this explanation of the shape of the peak shape response is almost similar to the LSB. So the initial region is due to the initial rise in rapid rise in current is due to the electrokinetics, fast electrokinetics, and the peak shape is due to the concentration gradient or due to the diffusion control, mass control process. And from here, when we go a negative or maximum potential, we will reverse the scan to a minimum potential, and we will see when it reaches the potential of equilibrium, reversible potential, it will start to re-oxidize the product produced in the preceding scan. And reverse reaction is occurring. Here the maximum electrode kinetics can be found, and then from here you will see the fall of current, and this is due to the mass transport process. And if we consider a typical reaction, we can see here reduction is maximum reduction, and here maximum oxidation is occur. And how, if we change the scan rate of the experiment, this is for example for a single scan rate, and now if we change the scan rate for like ferrocene, like ferrocenium product, ferrocenium analyte, and we change the scan rate from 50 to 500 millivolt per second. Similar to LSB, we will see the peak current increases with increasing scan rate. It is at any given for any system. It could be reversible, but the trend in changing current is similar. It will obviously increase with increasing scan rate. So how we actually interpret the data? We can interpret by taking a CV, and we have to calculate several data to conclude that whether the reaction, the electrode potential, the redox process is reversible, irreversible, or quasi-reversible. First, have a look at the response or voltammogram. We can see a very two distinct clear peak in the measured potential window. So we can say it's reversible, but we have to confirm whether this is actually reversible or quasi-reversible process. So first we have to check, we can calculate the peak current using the Randle-Sevcik equation, which look like this at 25 degrees Celsius, or at any given temperature. It would be the peak current, whether it is cathodic or anodic, the equation will follow this. So what is peak potential? So peak potential, we can hear, sorry, there is adhan going on, so you may hear the sound of adhan. So we can wait a little bit. So we are back again. I'm sorry for the interrupts. So in Bangladesh, we have many mosques, and the sound can be heard from anywhere. The other sound. So now back to the point. So everyone have please give attention in this figure. So now let's start. We start from here. Our experiments from a potential where no redox process is happening, and then we go to a positive scan, which means we are now considering the oxidation reaction first, and we here the maximum oxidation occur, and we further continue to increase the potential where the current is diffusion control limited or mass transport limited, and then we switch the potential to a negative value where the product produced here start to reduce in this potential scan, and then here we will, when the equilibrium thermodynamically favorable potential is reached, the electro reduction becomes more faster and more favorable, and current will increase very rapidly, and we will see a peak shape where the maximum, this peak is due to the here the current is due to the diffusion or flux of the analyte, which is proportional to the concentration gradient, which means change of concentration with the distance dc by dx, if we say it mathematically, and then we will come back to the initial potential. So this complete cycle have some characteristics, parameters. Then at first we look at the forward scan, which is oxidation scan, and we will see at this potential the maximum peak current observed at correspond this potential. So this is known as anodic peak potential, and this value of current, which is calculated by subtracting the background current, which is a tangent from this initial current response, and this value is known as anodic peak current. In contrast, where if we did not allow we did not apply or we did not scan the potential reversibly, is just a simple LSB, we could not see this peak. On that case, the current will decay like this, and we will plot a tangent from here, and we subtract this current value from this peak value, and we will calculate, we will say this current difference is a cathodic peak current. So be careful, it's not from here. Cathodic peak current cannot be calculated from the initial current value. It should be calculated from here, where the actually current falls from the preceding cycle. And now the calculations, the equations, and some other, before going to calculations, let me show you some note of a reversible system in reversible cyclic voltammetric system, where some phenomena we can observe easily. The peak potential is independent of scan rate, and peak potential is independent of concentration, analyte concentration, and peak potential and peak current is at any given scan rate or at any given potential. The peak current actually proportional to the square root of scan rate. So this type of phenomena you will see in a reversible system, cyclic voltammetric. So now that how the equations, we can treat the equations like peak current, peak potential, and other parameters. So at first, let me show you the peak current, how we calculate or how we treat the peak current. And we use Randless-Sepsic equations for this calculation, and the equation is look like this, and where the symbols, what the symbol means, and their unit is given here. And next, let's move to the peak potential, how peak potential is calculated, what type of parameter we can find from peak potential. For a reversible system, peak potential is actually, we can calculate from these equations, and where and sometimes the peak potential, the peak is a little bit wider, and we cannot, it is tedious to measure exact peak potential. So often we calculate half peak potential, which is represented as EP half, and at where the I is actually IP by 2. So at EP by 2, that equation follows like this. And what is E half? So it is the halfway potential. It's a characteristics of any metal or any analyte or electrode, we can say. And this, for reversible system, this is just located midway of peak potential and half peak potential for reversible system. And if we check the peak separations, and we will see for the reversible system, peak separation is almost 57 millivolt. If one electron transfer is considered, and if the electron transfer is more than one, we can input the value of number of electron transfer here, and we can calculate what is the peak separation. So, and next, this is for only a reversible system, and for irreversible system, the equations, the phenomena will change from irreversible. So in this slide, we show how to interpret or how to treat the data of a cyclic voltammogram, which is shown here. And we can see that we will calculate, we will have the data of peak current, peak potential, Nernstian equations, and half peak potential. We can also calculate another parameter which is very much known, very well researched parameter for any electrochemical system. Any electrochemist would like to measure the diffusion coefficient of the analyte or of the compound which is going to investigate. So how diffusion coefficient will be calculated? So if there is a sigmoidal or a steady state curve, like equation, if the signal is steady state, depending on the experiment conditions, or depending on the viscosity, molar mass, or scan rate. So equation will be like this. If we have a peak shape response, peak shape curve for CV or LSB, the equation, we can plot the current versus square root of scan rate, and from that slope of that data, we will calculate the diffusion coefficient using this equation. So how can you relate this diffusion coefficient is to actual value? So you can compare the diffusion coefficient using the Stokes-Einstein equations. This is you can see the data of like viscosity of the electrolyte and other size of the diffusing species, and at constant temperature, you can easily calculate these Stokes-Einstein equations, and you can compare if the experimental data is almost accurate or not. So for your consideration, here is a typical response. Let me show you, like, for a reduction process, and this is actually reduction of cobalt in aqueous system, and we will see only IPC. Look on the IPC, cathodic peak current, and we can measure the cathodic peak current with increasing scan rate, and we will plot data of IPC versus the square root of scan rate, and from this data we can easily calculate the slope by calculating difference between two data from the graph, and dy by dx, and from after we measure this slope and we put this value in this equation, we can calculate the diffusion coefficient, and we can also plot another graph, current density, which is proportional, inversely proportional to the square root of viscosity of the system, viscosity of the electrolyte. So you will see a straight line passing through the origin, and you can also measure the diffusion coefficient from here as well, from the slope of the graph. So finally, we can conclude for a reversible CV, what type of diagnostic information we can obtain from a reversible CV, what type of consideration we have to make before commenting whether the reaction, whether the cyclic voltammetry is reversible or not. First, have a look at IP, peak current is proportional to square root of scan rate, and next EP is independent of scan rate, and the separation of peak potential and half peak potential is about 57 millivolts, which we can say the peak separation, cathodic peak current and anodic peak current, is about 57 millivolts for a single electron transfer at any scan rate. And the ratio of cathodic peak current and anodic peak current is unity for reversible system. So if when you see a cyclic voltammogram and you analyze these parameters, and you can easily say that whether the reaction is reversible, whether the reaction kinetic is fast or not. So what if we cannot see the reverse peak in the measured potential window? Sometimes it happens, and where the backward reaction rate is negligible, then forward reaction rate, and we will not always see the backward peak as seen here. So if the reaction is irreversible, for example, forward reaction is occurring, if the cathodic reaction is occurring only, then we will see a cathodic peak, and in the reverse scan, we cannot see any other response. So how you will treat the data for irreversible system? Yeah, at first, have a look when the irreversible system is concerned. We must think there is a kinetic, sluggish kinetic, then a reversible reaction, and there is a electron transfer a term alpha electron transfer coefficient, and a term kinetic constant should be introduced. So the relationship of peak potential and peak potential with half peak potential will be changed from what we see from the reversible system. And how it will change, you will see this equation, and how the current will be calculated for a irreversible system. You have to consider about this relationship, where a new term alpha is introduced instead of n, and what kind of phenomena you will observe in a irreversible system? Yeah, actually, you will see a very well separated cathodic anodic peak, and the current will decay with inverting the sweep direction. So, and then you will see the peak potential is dependent, where the reversible case, the peak potential was independent of scan rate or sweep rate. Here is dependent, is very much dependent on sweep rate. And when we apply more scan rate, for example, 1 volt per second or more, the reaction characteristics will become more irreversible. So if we allow less time for the product to re-oxidize or re-reduce, there will be no reverse peak, and we will see a very irreversible system. And there will be a shift of EP for reduction in a negative way about this amount at 25 degrees Celsius for 10-fold increase of scan rate. So if we increase scan rate 10-fold, the shift will be about these values. So next, let me discuss about quasi-reversible system. And what is quasi-reversible system? So sometimes it is not so straightforward that we can see that forward reaction is faster and backward reaction is negligible, and sometimes the reaction is in between. So we have to consider forward reaction rate, we have to consider the backward reaction rate as well. So we may see a reversible peak, but the peak is widely separated and peak current intensity relatively decrease compared to the reversible systems. Now have a look at here. If let me say that this black line is the signal for a reversible couple, O2R couple, and this dotted line is should be it's a typical line for a quasi-reversible system. So you can easily see that there is a large separation of peak potential, and the current signal is relatively lower than the reversible system. And we need more over potential, which is the difference between formal potential to applied potential for a quasi-reversible system. So, and another phenomena you can observe that peak current will not be any more proportional to the square root of the scan rate. So using looking at this features of any voltammetric data, you can say that what kind of reaction, electrochemical reaction is occurring at the electrode surface, and you can also calculate the concentrations, calculate the diffusion coefficient, and other many important parameters like half-wave potentials and many more. So Dr. Prastika maybe can show the input of voltammetric, especially cyclic voltammetry. The student will be very more familiarized with how to input the data. What do you say?
Yeah, sure. I'll try to show.
I stop here.
Yeah, please. Okay. Please wait. Okay, is it clear? Okay.
Yep.
Yeah, so this is just one example of a software from the potential start pump sense MSAT 3+. So this is the basic software, and this one is this is square wave voltammetry, but I can change. For example, we have some technique from Dr. Shamin. I think it's already explained before,
Mhm.
like linear strip voltammetry and then cyclic voltammetry and so on. And for example, if we choose cyclic voltammetry, and in here we can input such kind of
initial potential. So So initial potential where the no Faraday process is occurring, reduction or oxidation is occurring, it could be the open circuit potential of that system, reversible system. And then depending on whether we will study the oxidation or reduction, we will scan positive direction and then we will scan to a negative direction. And then we will put the scan rate, how we will change the voltage or applied potential per unit time here, and then how many cycle we will scan. So we can use 1 cycle, we can use 5, 10, so on. So this is how cyclic voltammetry data input, and then maybe this is the square voltammetry, no cyclic voltammetry data here. So square wave voltammetry. So if once we put this data and we start the measurement, you will see the response here. And from the response, you will, looking at the response, you can say whether you can assume whether you will get reversible, irreversible, or quasi-reversible data, and then you have to analyze electrochemical parameter to confirm your assumptions. So thank you, Prastika. So let's move on. So I might be slow a little bit. So, yeah.
Okay.
Okay. So from us sweep techniques, so now we move to step techniques. What would be the step techniques and what would be the advantage? So from step techniques, again we can deduce the electrode reaction and their rates, and we can also reduce the capacitive current component from the Faraday component. And what we will do in a step technique is just we change a initial potential where no Faraday process is occurring to a potential more negative in case of reduction, that where the current is solely dependent on mass transport. And this step is instantaneous step, and the current at that for the step, the final step, will be calculated using Cottrell equation, which can be shown as here. And what type of like experimental setup we can use a simple potentiostat, and we can use 3 electrode system, and we can step from initial potential to a final potential, instantaneous step, and then we stay a little bit time on that final potential, and we will see the current response. So next slide. So here now look the same similar like for a simple reduction reaction where there is no reduction reaction, and here is a complete mass transport region. So this instantaneous shift of potential will cause a instantaneous increase in current, very high amount of current, and then we will hold here for a second, for a couple of seconds, and we will see the decaying of the current. And how we can explain this decaying of currents with the concentration gradient. So look at this figure. When initially when we change the instant potential, we increase the potential at that region that almost analyte close to the electrolyte is consumed, and after that the analyte must be diffused from the bulk to the near the electrode surface, and we will see the decreasing concentration gradient. And with time, the current, since current is proportional to the flux or concentration gradient, so with time this concentration gradient is decreased, and consequently current will be decreased. And how you can calculate, as I said before, it is calculated using Cottrell equation, and this kind of experiment is known as chronoamperometry, where chrono means time and amperometry is we are no more measuring current versus potential. We are keeping the potential constant and we are measuring current as a function of time. So this name came from that relationship. So this is can be named as a one-step chronopotentiometry, where we can study either oxidation or reduction of a chemical species, electrochemical species. Now, there are techniques where actually we can also analyze or we can study the product using which is named as double step chronoamperometry. Before going to that, we will see if we do a series of step measurements. That means we will start from a potential where no Faraday reaction occur to a potential where Faraday reaction start, or electroactive, the chemical become electroactive. So we do series of experiments. Every time we instantaneously step to a potential, then finish that experiment, and then we start another experiment from the same base potential to another step potential, and then we complete that experiments, and we do so on. Now, consider that the step 1, where the no Faraday reaction occurs, actually there is only capacitive current. So the signal will be shown as like this, current versus time signal. And if we state the potential in a region where the chemical is now electroactive, and they can go to the reduction reaction, but still not the maximum reduction reaction. The rate is not maximum. In that case, we will see the current decrease from an initial value, and with time it will decay. And for another potential, like for 3, for example, that we will see the change in like this. And now we step more to potential where the current is, or where the reduction is completely mass controlled. The reduction is no more electrokinetics, is almost the diffusion of the flux from the bulk to the electrosurface. And in that time, we will see the for 4 and 5 almost same current versus time response, because the condition is almost limited. So for any given time, any given sampling time, if we pick a sampling time, for example, tau, and we draw the data of that time, that preferred time, predetermined time, we draw the current versus applied potential, step potentials. Actually, from here to here, this value to increase this value from here to here. And we will see a sigmoidal shape response for a sampled, this series of step techniques also named as sampled current voltammetry. And we will see a sigmoidal shape response where we can see this is due to the non-Faraday current, and this is due to the Faraday 2 and 3. And for 4 and 5, we will find the mass transport current. And this is how sampled current chronoamperometry can be conducted, and how the response look like. So the next, as I say before, we can use a series of step techniques to check the current time profile, current potential profile, and we can calculate many parameters like using Cottrell equation, we can calculate diffusion coefficient, and we can also conclude about reaction rates, redox properties as well. And now if we step the potential from a potential where no redox reaction occurring and a potential where redox reaction is occurring, for example reduction, and then we stay here for a couple of seconds or milliseconds, and then we come back to the initial potential again, or we can it is almost similar to the cyclic voltammetry. We go for in a one direction, forward direction, and then we come back to the backward direction. So similar to the cyclic voltammetry, we will see the two signal. One is for forward reaction, forward reaction where reduction were taking place, and once we we switch the potential from E2 to E1 instantly, we will see a drastic rising current, which is anodic current, and we will stay here for a little bit. We will see a depletion of a current, and this is due to the depletion of diffusion layer and the transport. So we can easily analyze the product produced in the forward reaction, and we can consider the stability if whether the product is stable or not from measuring double step chrono amperometry. Next step technique is we now instead of current, we can integrate the current. Actually, we can measure the variation of charge, how much charge is consumed, how much charge is produced during the electrochemical reaction as a function of time. So this, since this is measuring the charge, which have unit in coulomb with time, which the chrono means time, and then this technique is named as chronocoulometry. So what is the advantage of chronocoulometry? So from this technique, usually we can separate the contribution from Faraday current, contribution from double layer current or charge, and if the electrode have some absorbed species, they will also contribute in the current. So if we consider any step technique, we can say the current for a planar electrode, current will follow the Cottrell equation, which from here, if we plot the charge against t square root of time, we will see a straight line passing through the origin. From this equation, actually, this should be passing through origin. But in practically, this never goes through origin. There is always an intercept there. So how why this intercept appear? Because there is not only Faradaic charge, there is non-Faradaic charge contribute to the response. What type of non-Faradaic charge? It could be capacitive due to double layer, or it could be charge due to any adsorbed species which also undergo the reduction. So actually the equation will be modified from here to here, and you will see the response like this, or we can explain a little bit more like this, and how you have to calculate the total charge, and you have to eliminate the charging component, you have to eliminate the absorbed species charge from absorbed species. Now let's move to another step techniques, which is known as pulsed voltammetry, which is actually a straightforward technique of chronoamperometric techniques, where potential was stepped and current was measuring as a function of time. And here we will step, actually it's like sampled potential step. We will step from a base potential to, and we will increase the step potential linearly with incremented step. And we can use any static electrode or dropping mercury electrode for this type of voltammetry. So when we will use mercury electrode, this voltammetry will be named as pulse polarography instead of pulse voltammetry. So here is a schematic representation for pulse polarography, and you can see we will have a potential state which is very well programmed to supply potential or to supply current, and we will have a pulse sequencer when to start the pulse, when to hold, when to back to the initial, and we will have a drop knocker which actually control the burst and drop losing time, when we should start the experiment, when we should stop there, depending on birth and drop of the mercury drop. And we will have converter and recorder. So basically, this pulse voltammetric techniques will be a computer controlled. There will be computer control. There will be very well software which actually program all these things. So you actually, what you do is just input the potential where you want to pulse, how many time you want to hold. There will be a window, input window, and you will just start the experiment and you will see the response. So now move to how actually the principle. So what is the principle for, there are many types of pulse voltammetry. For example, normal pulse voltammetry, reverse pulse voltammetry, differential pulse, and square wave, and more complicated ones. So today we will discuss three of them. The first, normal pulse voltammetry. So what it do, it actually series of pulse, we take series of pulse and we increase in the amplitude of the height of the pulse with a definite or with a certain amplitude. So we start from a base and then we step to a potential, final potential, and we will hold a time which is known as pulse width, the operational time, and then we will come back to the base again and wait a while where the diffusion layer is renewed again, and then we step to a little bit higher potential and come back again to the base. So we will sample at what point we will sample the current. Actually, we will sample the current just finishing the pulse, just ending the pulse somewhere right here. So actually about 40 milliseconds we will stay on the pulse potential, and then we will measure we will take the value of current, and once we complete several pulse and we plot the data, current versus voltage, we see a sigmoidal graph which can be very similar to sampled current voltammetry. So because the first pulse is not so enough to reduce or electro-oxidize the analyte, and with successive increase we will shift the electrode potential to the more negative or more positive than the reversible equilibrium potential, and the current will increase, and after that there will be mass transport region, and the current will become static. The current will no longer dependent on the potential. So using these techniques, NPV, we can actually minimize the charging current nearly zero, and we can say the response is solely due to the Faraday process. Now let's move to another voltammetry, differential pulse voltammetry. So which is almost similar. We have to increment the pulse, but what is different from NPV is like base potential is no longer similar to the previous pulse. So every time our base potential will be incremented, increase from the initially, and this increment will be symmetrical. So we will see a signal, excitation signal like this. And when to sample the current in difference voltammetry, sample current twice, once just before the pulse when we start the experiment, and another one just before ending the pulse, before dropping the pulse. And we our computer control software will measure the value of difference of I2 minus I1. Current responding here corresponds to here, and current corresponds to here, and we will see the data graphically as a current versus voltage. And this is the schematic experimental setup. So actually we have very well known setup with computer control program. So they will do everything. We just need to set our electrolyte, and we input the data, and they will do all this for us, and they will give us the signal directly in our monitor. So how to interpret differential pulse voltammetry? So it is like a staircase voltammogram, which is the schematic representation can be like here, and we will symmetrically increase the step, and we will superimpose with a pulse with staircase voltammetry. So in normal pulse, the base will be the same, but in differential pulse, the base will be increasing like stair. So look at here. So at first it was a base stair, and then we superimpose a pulse ramp, potential ramp on it, and we will sample current here and here, or here and here, here and here. So every time the computer control program will differentiate this from this value to this value, and we will have a peak shape response rather than a sigmoidal response than in NPV. And the peak potential will have the equations similar to this. And since the delta E, peak amplitude, we cannot go a peak amplitude more than like say 50 millivolt from the initial value. So if we start, for example, from here is 1 volt, and from here it should be 50 to 100 millivolt. We cannot go there. So if we go more than 100 millivolt, the accuracy will be drastically changed, and we cannot find the good data. So so if we assume this value is very much small compared to this value, and actually peak potential will be characteristics of half peak potentials, and peak current from DPV will calculate from a modified Cottrell equation, where you will see the sigma, and what is T and tau is, you can see here how to input the time, how to calculate the time parameters, and what is sigma here. This sigma here is corresponds to this these equations, and the maximum value for this ratio should be unity. And another parameter we can measure is peak width at half height. When we consider half height, this around half height, how will be the peak width? The equation will goes like this. So using these equations, we can measure parameters, and we can calculate, actually we can calculate the parameters from DPB, and we can calculate concentrations, so we can calculate the diffusion coefficients, current potential relationship, and so on. Now let's move to the another session, which is square wave voltammetry, one of the very widely used techniques in electrochemical analysis, which is very much advantageous than NPV to DPV in the terms of sweep rate. Square wave voltammetry can be swept much more, and so time is less time, and we can actually analyze concentration vary down to around 10 power -8 or sometimes 10 power -10 molar concentrations, and block diagram for square wave voltammetry is almost similar to the any pulse techniques, as you see from previous slides. And now let's move to the data interpretation, how potential excitations looks like. So this is we have a staircase base potential, and we have to superimpose a pulse, but this is a reverse pulse. So what we will do, we will have a base staircase, a base pulse, and we will impose a pulse on it. But this we should not increase linearly. We will go a forward scan, and we will step from a potential where no Faraday current found, and to a potential where the Faraday current is maximum. And we will sample the current at the just before ending the pulse, forward pulse, and then we will go back to a reverse pulse, and we will go down very reverse potential, and we will wait here a little bit, and we will sample the current here. So here some parameter. This time is from here to here is called the pulse width, which is denoted as TP. And for a staircase shift from the base to staircase shift is delta ES, and from staircase height to the actual height is pulse height is delta EP. And how the square wave frequency and scan rate is related is given here, mathematically given here. So how is signal look like in square wave voltammetry? So since we are using a staircase base and we superimpose a reverse pulse on it, so we will see a reverse current where forward reaction is occurring, and we will see a forward current where the first forward reaction is occurring, and we will see a reverse current for reverse pulse. So it's almost similar to cyclic voltammetry response. So, and then the program, our software will measure the difference current from forward current to reverse current. So if we plot a dimensionless square wave voltammetric current function with applied potential, we will see a forward current for A and backward current for B. This is actually the reverse reaction, and the sign will be the reverse, and the difference current we will subtract the current from here and subtract from this value and subtract from this value, and we will actually find our voltammetric response will be given here. So Dr. Prastika previously shown actually a cyclic square wave voltammetric data, and you have seen the peak shape data actually there. So this is for a single electron transfer, single step. So if there are more complicated step is present, so you will see more peak on onward, and if you can go more negative or go more positive to see if another reaction is occurring or not. So how the parameter peak current will be calculated, or how what parameter they depend? Actually, the peak, the current, dimensionless peak current depends on several parameters like peak width, peak pulse height, and shift, staircase shift, and peak current density will be calculated, modified Cottrell equation, which is shown here. So this is overall. After discussions of up to now, there have been many heavy metals, organic have been analyzed or have been detected on very low concentration. And here are some examples, how they, at what range they calculated, and there are some techniques, what type of techniques can be used. So you can see here, and let me conclude at a glance how actually, so what is the principle of each techniques. So CV and LSB is we have to scan the potential and we will see the current versus potential curve, and for chronoamperometry we will see current versus time curve, and for pulse voltammetry we will see the current versus potential time, which is very similar to amperometric techniques. So thank you for your kind attentions. Now, if you have questions or comments, let me know.
Okay, thank you very much, Dr. Sarmin, for a nice presentation. So let's giving applause reaction to Dr. Sarmin. Yeah. Well, voltammetry actually is not really generally known, or it's not in industry, for example, or in research. It's not generally known like a chromatographic, spectrometric, or maybe electrophoretic. But this voltammetric, well, for specific analysis, it's offers superior solutions actually. If some reactions contain voltage and current, we can know the mechanism and etc. So Dr. Samin has already summarized the basic concept of voltammetric data processing, and it's very useful later for your research in electrochemistry. Okay, so now we're going to question and answer session. All the participants can answer or give a question, by raising your hands, or you can leave in Zoom chat. Okay, so let me see if somebody asks this way. Oh, here, Farhan. Yeah, Farhan, please.
Thank you. I want to ask about, I'm sorry, can you hear my voice?
Yeah, sure.
Oh, yeah, thank you. I want to ask about the LSV. So if we don't get a single peak when we're using LSV method, so how we can conclude the data from our research? And then, is there any reason why this kind of things happen?
Sorry, your answer is, your question, can you
maybe one more time.
Okay. I want to ask about the LCV method.
Okay.
So
LSV. Okay.
If the LSV method, we don't get any single peak when we using the LSV method, so how we can conclude the data from our research?
Okay.
And then, yes. And then the second question is there any reason why this happened? So when the LSVs, there is no single peak, what kind of things that happen in that our data?
Okay. So if the reaction kinetics is much more complicated than single elementary step, we have a electron transfer containing consecutive step. So, like for example, we will have total 4 electron transfer total. So at first step, you can see a 2 electron transfer reaction, and then this reduced product will go further reduction and 4 electron transfer reduction. So you will see a consecutive peak instead of single peak. And in some case, you may not see the peak if you choose the final potential as where the reduction is not possible. That means the reduction potential is not negative to the reversible potential, chemically, thermodynamically favorable potential. So you have to go beyond this value where the actually reaction is favorable. So if your final potential is kept below there or somewhere near, so you may not see the peak shape or may not see the signal. You will see just a little bit current, like a straight line like this, or almost close to zero. So like this. So you will see, and this was your question. So when you cannot see the peak or for a single peak right now, and then next it was like how is did you get the point?
Yeah.
For
About the first point, I get a little bit the point that
and
then the second question.
Okay, continue.
The second question is there any reason why this kind of things happen?
Okay, why happens? So let me again explain. So if the reaction is not like very simple, straightforward, one electron transfer or only single step process, this like this. So you may have multiple step reactions. Like there are many steps, many electron transfer steps. One is, for example, you will produce like R, and then these R can go further reductions. So you will see the another peak or the deviations from this kind of peak. So or there will be another reason that reaction is coupled with some chemical reaction that is known as homogeneous coupled reaction, and that kind of electrode reaction is known as EC reaction. That means electrochemicals and followed by chemical reactions. And there might be another reason, that ECE mechanism. That means you have electrochemical reactions, then chemical reaction, and then finally you will have electrochemical reactions. So this this may cause the change the normal signal to a very different response from the theoretical values or what we know from theory. So depend on reaction mechanism, depends on the electron transfer process, whether it's a single step process, whether it's a multi-step process, or whether there is some absorbed species is present at the electrode initially. So this will also, absorbed species will also reduce. So you will find another kind of parameter, another kind of response there. So yeah, you will see there will be many reasons behind that. So our we can analyze each peak, and we can compare with the chemical reactions, with electrochemical reactions. So yeah, you so
Okay.
hope you get the point. So
maybe like the most what is it, the bad situation is that the electrolyte or everything is not electroactive.
yeah.
Example that you analyze is not electroactive.
Yeah, that was I maybe answered previously.
Yeah. So okay, Farhan, it's okay. Thank you very much, Dr. Sharmin. Okay, Farhan.
Thank you for the answer, Doctor.
Okay. Okay, let me see if somebody raise your hands. Yusrama Deni.
Okay, thank you very much, Dr. Prastika and Dr. Sarim. Amazing. Actually, honestly, I'm a newbie in CV voltammetric. So my result is about solar cells. I want to try to see is it we have a chance to use this product, this machine, to understanding about the DSSC solar cell. Okay. I have two questions. The first question is, I'm confused which one is much better, instruments much better, because in my knowledge, actually we have two kinds of the electrodes. One, the conventional electrode, another one is screen printing electrodes. So based on your experiments, Dr. Sarmin, which one is much better for giving understanding about the CV voltammetric in a solar cell area? Another one is, I'm not sure, can we use these machines to understand the solar cells effect in case be using organic material like PDOTs and other things. I'm still confused about that. Thank you for
Okay.
your understanding.
So, which electrode is better for solar cells? So it depends on. There are many kind of solar cell, I think. Dye-sensitized solar cells and many other classifications, and we can use like ITO or many other electrode. So actually, it is not that straightforward to comment that which electrode gonna be very effective. So if for my best of knowledge, if we use maybe modified, electrochemically modified, especially if you can modify it with nano material, so that will give you better response. To best of my knowledge. So screen printed is good technique, but it is little bit complicated and little bit expensive than electrochemical process. And electrochemically modifications, you can just reduce or oxidize your interest material on a substrate, on a solar material substrate. We use like PN junctions and so on. And yeah, to analyze your electrode material, actually, the cathodic or anodic material, you can use the potentiostat. Maybe you have some potentiostat, so it is okay to use any of the potentiostat. And for organic materials, to analyze organic materials, you maybe use cyclic voltammetry, and the two. Up to now, the best is so far differential pulse voltammetry to analyze especially organic materials. So you may try differential pulse voltammetry to check the organic materials, and you may try electrochemically modified electrode for DSC solar cell. And yeah, you can use the potentiostat you have to check the material, and you can conduct the experiment like CV or DPV or any other techniques, so to analyze the material as well. So
okay, thank you very much. So, based on your explanation, so the conventional electrode is much better to do the experiments, yeah, compared to the electrode.
Yeah,
so you can modify it.
Yeah, you can electrode. Yeah.
Okay, thank you very much, Doctor.
Okay. So, okay, thank you very much, Mr. Denny, for the questions. Okay, we're going to the next. Here there is Akil Nova Rizola. Please.
Okay, excuse me, can you hear my voice?
Yeah.
Okay, my name is Akil Fariskullah. I'm a student from Nanotechnology Engineering. So I want to ask some questions to Dr. Sharmin. So why each element can have a different technique in practical uses of voltammetry? What will happen if we do the voltammetry with different technique or not based on the table? And my second question is, has this voltammetry been implemented in various places like industries or something like that? Thank you.
Okay, so maybe Dr. Prastika already explained that this voltammetry is not so much widely used in industry so far now, but we are now changing. This trending is becoming change, so we are now analyzing like solar cell, fuel cell, and we are also use like electrolysis in chloroalkali industry. So there are much more electrolysis you can use to separate the metal or to produce the caustic soda in industry. And another question is what type of voltammetry you can use, like not based on this technique. So there are many other voltammetric techniques, basically classified as control potential, control current. There are much control current techniques which is called chronopotentiometry, and you can use that techniques to actually read the battery system. You can check the cyclability to check battery. Chronopotentiometry, which is named as chronopotentiometry, which is control current. Current is controlled and you measure the potential as a function of time. And there are other techniques like which is in pulse voltammetry, which is known as reverse pulse voltammetry. What we do is we start from diffusion control limited region to a region where no Faraday process is occurring. So you can use that also to analyze the product or to check the accuracy of the reactions. And you may use first scan cyclic voltammetry, and there are many modifications like inclusion or introduction of FT method to cyclic voltammetry, which is known as FT cyclic voltammetry by FTCV, and so on. So there you can use many other techniques, like electrodeposition is another technique. So you can, what you use, that you hold a constant potential for a predetermined time, for example, a couple of hours or couple of minutes. So you can do that experiments and then analyze the deposit using some other spectroscopic techniques as well. So yeah, you can use many techniques, and industry we will use in industry. So we are now moving to electric cars. So there are very much scope to electrochemists to work on electric car to reduce the pollutions and to reduce the using fossil fuel. We are now in energy crisis. So yeah, you got that?
Yeah, I get it. Thank you very much, Dr. Sharmin.
Welcome.
Okay, thank you very much. We're going to the next questioner. Here there is Agustina Octaviani, please.
Hello, Dr. Samin.
Hello.
I'm Agustina from Nanotechnology Engineering. I want to ask, on the third slide, it is explained that capacitive current is non-Faraday current that contributes to charging of the double layer capacitance. What is the double layer charge time constant, and how far is the double layer from equilibrium, and what is the effect on the equilibrium curve? Thank you.
Okay. So your question is here, what is equilibrium constant? So equilibrium constant is for a couple, like chemical couple from A to B, the reaction is going to A to B. There is a thermodynamic potentials which allow, with thermodynamic potential, the reaction is possible, favorable to occur, and this is related to Gibbs free energy. And the equations you can write is like potential equal to NFE. That potential N means number of electron transfer, F is Faraday constant, and E is the potential. So delta Gibbs potential is equal to NFE. So if a reaction is spontaneous to occur, so delta G value must be negative. So to correspond this, that delta Z value, there will be a equilibrium electrochemical potential value. So that is different for every different redox couple. So that is known as the equilibrium potential. So, and in another term, so what drives a electrochemical reaction proceeds? So if we look at the potential at this electrode, which is, for example, denote as a electrode potential, and the solution have electrolytic solution have another potential to move through the electrode. So this applied potential should be about the difference between this value, metal potential, minus the solution value. Solution have another chemical electrochemical potential, this value. So this is called the equilibrium potential. So theoretically, at this equilibrium potential, reaction must happen, either oxidation or reduction. But in practice, it is seen that at this potential, the reduction is not that predominant, not that is identified with any voltammetric technique or any analysis of potential state signals. So what we need to do, we have to shift negatively or positively. So negatively, when we are going to study reduction, so we have to move from that reversible theoretical thermodynamically favorable reversible potential to a negative value, to a much more negative value, to reduction to happen. So this is called the shifting of electrochemical potential value to a more negative value, and this difference of applied, so we have to apply more potential, so this is called applied potential, and the difference from applied potential to the thermodynamically favorable potential, this difference is known as over potential. And for your information, for a reversible system, any reversible system, that over potential is not so much more. But in case of irreversible system, we have seen that over potential, we have to apply much more over potential. Otherwise, irreversible kinetics do not happen. Irreversible peak, we cannot see the response in irreversible process. And quasi-reversible is in between reversible and irreversible process. So, and for double layer, the thickness of double layer depends on how much time you are allowing to electrolysis. If at a constant potential, you hold this whole process for a longer time, so this depletion zone will increase, the depletion zone area will increase, so thickness will be increased. So when the diffusion layer, this diffusion layer containing up to this, we can say the diffuser until around here, and there is a bulk region. Once the diffusion layer become more thick, it would be much more difficult to analyze, pass through this region to go to the electrosurface and electrochemically reduce or oxidize. In that case, the flux or the diffusion will be slow. So you will see a very decreased current with time. And how much thickness of this electrode, it depends on system. For a static electrode, the diffusion there is around, I think, nanometer level, 50 to 100 nanometer. But if you use hydrodynamic system where the electrode, you can rotate the electrode at a constant rotation per minute, in that case, you will maintain a very fixed diffusion layer throughout the electrode, whatever the time you are applying, the diffusion layer, this layer will be very fixed, and it will be several nanometer. It depends on viscosity of the electrolyte, depends on area and other parameters you analyze. So it could be a few nanometer, 10 to 15 nanometer, or in general, if the diffusion layer actually not longer than 100 to 200 nanometers. So yeah, that's the difference, how diffusion layer change with time and how concentration gradient will change with time.
Okay.
Thank you.
Okay. Thank you very much. There is more, some more questions. There is here Bayu Firmansyah, please.
Hello, Dr. Sharmin. Hello, Ms. Prastika. Can you hear my voice?
Yeah, sure.
Well, actually, I am still confused about the difference between the reversible and irreversible cyclic voltammetry. So, can you describe the characteristic that distinguish between the reversible and irreversible cyclic voltammetry, please?
Okay. So the reversible term, if you see it literally, that means you will you have a forward scan and a reverse scan. So when the reaction is reversible, and forward reaction and backward reaction can occur at a at a faster kinetics, and both kinetics will contribute to the current response. So you will see a forward current response, and also in the backward scan you will see another response. So this means you are seeing two signal, one for oxidation, another for reduction. So this means the forward reaction and backward reaction both are contributing current simultaneously, and both contribution are equivalent and equally important to get the signal. So this is, and how to characterize. Sometimes our eye cannot just look at the figure and say, oh, here are two peaks and one is forward peak, one is reverse peak, so it must be reversible. So that's not the case. Sometimes some quasi-reversible system can have a peak on a reverse scan. And what will happen in irreversible case? So when you use the same potential window, for example, some another chemical, when you go back here and then you switch the potential from here to and come back to initial potential, you will no longer see that the reverse peak. You will see just a background current here. So that means the backward reaction, the contribution from backward process, the backward rate kinetics is very much slow or very much negligible, that it could not contribute in the current. And you know from the current equations, the current is proportional, cathodic or anodic current is proportional to the concentration and F, electron transfer, area of the electrode, and also the rate kinetics, Ka or Ko or Kr. Ko means kinetics for oxidation, Kr also kinetics of reduction. So current will depend on rate constant and also concentration of the analyte. So once the rate constant value is very negligible, you will no longer see the reverse peak. So what will be the characteristics properties for reversible? The what we measure, the parameter, what parameter we measure, and we can say that it is whether reversible reaction system or irreversible system. So here are the mathematical calculations, how we mathematically interpret, how we mathematically treat the parameters. And these are some phenomena. And if we plot this data, we will see that peak potential, whether it is cathodic or anodic, will be independent of scan rate, which is also named as sweep rate, and will be independent of concentration, and the peak current will be proportional to the square root of scan rate. And we will see some other diagnostic information like peak separation, the separation from here to here. If we measure this distance from anodic to cathodic, this separation will be around 57 millivolts at any given scan rate at 25 degrees Celsius. And if we measure the ratio of anodic peak current and cathodic peak current, you will, for reversible system, you will find unity. If the system is not reversible, you will find the value of ratio of IPA versus IPC around 0 to 1 value. And for quasi-reversible system, this is also around 0 to 1 value. Maximum is 1, minimum is 0. So, and for irreversible system, another characteristics phenomena is the current equations will no longer have the electron transfer straightly. We can not say the electron transfer, we will say a electron transfer coefficient. And how you can measure? If you plot the current versus if you plot the voltage against the scan rate, you will see a that slope of that that graph will give you the value of alpha, and the intercept will give you the value of the rate constant. So from that analysis, this data versus scan rate, you will find the value of alpha and value of k, and you will look at the CV and you will not see another any reverse peak. And you can also analyze other, you can see this type of, you can plot this type of data, and you will see there is a continuous change of EP value with the sweep rate. which should not be appear in reversible system. And when you you increase the C rate more to a more value, you will see irreversibility will increase more and more. So, and for quasi-reversible, that is completely different. You will see a signal, a reverse signal, but that is not so prominent like forward signal. For example, forward current will be much more higher than the backward current or backward reactions. So yeah, and you will also find that IP is no longer proportional to the square root of the scan rate. From these characteristics, from this analysis, you will say this is, you will differentiate about reversible, irreversible, and quasi-reversible process. So,
thank you, doctor, for your answer. I think I need to learn more about this voltammetric because yeah, it's still a lot to learn.
Yeah, you will learn maybe more details not somewhere sometime.
Okay. Okay, thank you, Bayu. Okay, thank you, Dr. Sharmin. Actually, it's 5 more minutes, but there is 2 questions. Is it okay?
Yeah, that's completely nice.
Okay, please, Natalia Imelda, please.
Hi, Dr. Sharmin and Dr. Prastika. I'm Natalia Imelda Wulan, a nanotechnology engineering student. I have a question regarding DPV. What's kind of method that can be used to optimize DPV measurement, maybe by optimizing E-pulse and T-pulse?
What your question is DPV? Okay.
DPV.
And then what did you say? What kind of?
What's kind of method that can be used to optimize DPV measurement?
Okay, what kind of method? So in case of DPV, we have to consider that we should not increase the pulse and amplitude from initial point. If we start here and if we close here, we should not go beyond, for example, 100 millivolt to 50 millivolt to 100 millivolt. So we must look at that potential. We have to control this potential, and that allowing time, we can control this time, and it should not maybe a couple of seconds, 0.5 to 4 seconds, or maybe it may be down to microseconds. So these 2 parameters are very much of important in case of DPV. And also we have to check whether our system is correctly set up with the potential state, like our working electrode, where the reaction is going on is perfectly okay, is cleaned, is polished, and we have to use a large amount of supporting electrolyte to stop the migration. And we check the reversible electrode as well, whether the reversible electrode is working perfectly. So we have the accurate value of EP and halfway potentials, and the analyte doesn't have any contaminations. So we can, if there is a chance that oxygen can interfere to the reactions or water can interfere to the reaction, we must shift the reaction to a very vacuum condition. So this type of preconditions we must take care of. And we can go with the softwares after setup. We can go with the softwares and we input this data, and the rest will do by the computer. And you will collect the response and analyze the parameters or graph. So you will have the data, what you need, what you want to calculate, whether concentration or any other parameters.
Okay, Natalie.
Okay, I get it. Thank you so much, Dr. Sharmin, for answering my question.
Okay, thank you very much, Natalie. 2 more questions.
Okay.
From Harits Atika from Universitas Gunadarma, please.
Okay, thank you, Dr. Prastika and Dr. Sharmin. I'm Harits from Pharmacy Department of Universitas Gunadarma. So, Dr. Sharmin, if I read some articles for a pharmaceutical application using electrochemical methods such as drug sensing, they use CV for the optimization of the electrochemical activity, like pH dependent or not, how their kinetics, mechanism, and so on. But for the quantitative quantitative application, I mean for the calibration curve, they use DPV. Why it can be why they do like that? Why they not use DPV method for the optimization of their electrochemical activity?
Okay, so thank you. So one of the advantage of pulse is this is actually introduced to minimize or to the Faraday process, the Faraday current or non-Faraday current or charging current, which is mostly impossible with CV, and we can do it with very much sophisticated potentiostat or very well structures of software which can subtract the background current. But in case of DPB, the technique itself use the principle that it decays the what is going? It decays the non-Faraday current almost zero within a few microseconds only. So that is one advantage where in CV or other control potential method, the charging current cannot be eliminated completely. We can minimize it, not eliminate it. But in case of pulse technique, DPV, so we can minimize the charging current. And another great advantage is in case of drug, we use, when we intake the drug, we usually try to minimize the sample quantity in a nano or micro level. So the cyclic voltammetry program can detect the concentration in micro level or sometimes 10 power 4, -4 or -5 molar. But using pulse technique, actually DPV or square wave voltammetry, you can down the analyte concentration very much low to like 10 power -8 to 10 power -11. So your analyte, consumption of analyte will be reduced. So you will need less chemical to analyze. And another is the absorption, if the electrode is absorbed with some species, the decrease or that absorption reaction will appear. But in case of pulse technique, every waiting time here, once the pulse is complete, the double layer is renewed, electrode is completely renewed. So no absorb or no foreign material is available here. So you will get for every experiment a very new surface, a very clear surface to analyte. So that would be the another advantage. So you can choose what you want. Actually, you want to minimize the concentration, you want to minimize the current, or what kind of parameter you actually want to determine. So that's all. You want to remove the contaminations or not.
Okay, so you mean that we can do the application, the quantitative application using DPV, but we also can doing the optimization of the electrochemical activity using CV, right?
Yes. You see the whether is redox active or not using CV or LSB, and you can determine concentration or any other quantitative to a very low concentration with very high precise result using pulse technique.
Okay, thank you, doctor.
Thank you very much, Ms. Harris from Universitas Gunadarma for joining this webinar and for the questions. Okay, actually we are running out of time, but there is one more question, I think, from the students. Is it okay, Dr. Sharmin?
Okay, very much okay.
This is the last, okay, from the students. So, Diva Meisha.
Thank you, Dr. Prastika. In this section, I have a question for Dr. Sharmin.
I can't hear clearly.
Okay. Yes. Okay, I have the question for Dr. Sharmin.
I think there are
I hear some additional sound. I hear some additional sound somewhere. Okay.
Okay, I have the question for Dr. Sharmin. The first one is, based on the presentation before, is about voltammetric data processing, right? And so, in fact, what is the implementation of this voltammetric data, maybe for an electronic device, medical appliance, or others maybe that correlated with nanotechnology?
Yes,
Can you give me some example like that?
Yes, that voltammetric techniques are widely using in many devices. For example, we are assembling capacitors. We have to check the capacitive properties of the electrode. We are assembling battery. We have to test the properties of electrolyte, electrolyte used for battery, electrode used for battery, and this is also we use electrochemical test for fuel cell, membrane fuel proton exchange, membrane fuel cell. We also check the oxygen reduction reaction, water, carbon, hydrogen evaluation reactions, and also carbon dioxide reduction reactions. So there are many implementation actually voltammetric techniques, for example, CV or square wave voltammetry, and we also use to detect the trace heavy metals in industrial effluent, which throw many effluent with some contaminations with heavy metals like maybe samarium, like maybe any other zirconium that can be found in industrial waste, a very minute amount. So we can use voltammetric technique to analyze them, or we can test the water quality, like it have arsenic or some metal using voltammetric tests. Yeah, and so on. We can use in drug analysis, we can use in also supramolecular chemistry, or many more system to analyze the samples.
Is it okay, Diva? Okay, I see. And the second one is, I'm still confused when we use the CV1 or NPV like that.
Okay, when to use? So for you, like you have a electrolyte with unknown concentrations, so you may first try with a simple technique CV to check whether it is electrochemically active or not in that potential window. And once you can find the signals or whatever the reversible, irreversible, quasi-reversible signal, and you want to analyze more quantitatively, more precisely, you want to check the diffusion coefficient, you want to check the concentrations, or you want to check the stability, potential stability, or you want to check the cycle test. So you may change to pulse technique or chronopotentiometry, or if you want to also check how the surface phenomena, surface resistance, like bulk resistance, solution resistance, electrolyte resistance. So you may use impedance techniques as well, which I did not discuss here. That technique is also very useful to investigate the surface of electrolyte interface. So you can go with sequentially one by one to confirm your result, whether you are correct or not. So more techniques you can use so to compare your results with data.
Okay.
Okay. Yeah, okay, thank you, Dr. Samrin. It's very clear for me.
Thank you.
Okay, thank you for the questions. Okay, I think, yeah, we are late for about 10 minutes. Thank you very much for Dr. Shamin. We are so happy to welcome you here. And to all the participants also, thank you for coming. Hope this webinar can give you some insight in voltammetry data processing. And before we end this meeting, I think we should take a photo. So, Dr. Shamin, could you please close?
Oh, yeah, I'm just trying to stop. Yeah.
Thank you very much. So, all the participants, could you please open the video? So, we would like to take a photo here.
Okay.
For all the participants, please. Is there Miss Indah here? So Miss Indah is one of our lecturer in data analysis class. Miss Indah? Miss Indah? Miss Indah here? Okay, so okay, Miss Indah will help to take photo. Okay. Miss Indah? Okay, so maybe there is a problem with signal. Okay, I'll help to take a photo here. Okay, so for the first page, 1, 2, 3. Okay. Okay, for the second. 1, 2, 3. Okay, the third one. 1, 2, 3. Okay, and the fourth. 1, 2, 3. Okay, and the last. Okay, 1, 2, 3. Okay, thank you very much once more for coming in this webinar, video conferencing with Universitas Airlangga. We are so happy to welcoming you here. And once again, hope this webinar can give you a more insight to data processing in electrochemistry, especially in voltammetry data processing. So I close this webinar. Thank you very much. Good afternoon all. See you again in the next webinar.
Thank you, Dr.
Yeah.
Jessica. Thank you, Dr.
Thank you.
Thank
you.
Thank you.
Can leave soon.
Thank you, Dr. Prastika. See you next time.
See you. Thank you.
Thank you.
See you again. Dr. Sharmin, thank you very much. Yeah, thank you very much.
Thank you, Prastika, for inviting me and having the webinar with me. It was really nice to meet you.
Yeah. 久しぶりですね。
久しぶり。And ありがとうございます。
はい。Happy Ramadan also.
Happy Ramadan. Have a very nice day. And Assalamualaikum.
Yeah, Waalaikumsalam. Thank you so much. See you again. Bye bye.
See you again. Bye bye.
Thank you.